Welcome everyone to the third video of the COA lecture series. In today's video, we will know that integers, fixed point numbers and floating point numbers, how they can be represented as binary form. Okay, the binary data representation of these numbers. Binary and data. First of all, let us focus on these two terms. Binary, I think I am pretty sure that you all know this, that the machine only understands zeros and ones. These two bits are called binary digits or the binary bits. And the second term is data. Now data can be anything. It can be alphanumerical, it can be alphabets, anything. But here we know that computers are invented to operate on large numbers, right? So basically data here is a value, the numbers. So before landing in these two main topics, I want you to know about the BCD number system, binary coded decimal. In real world we use decimal number system. What it is, the 0 to 9, the 10 numbers are called the decimal numbers. With the help of these 10 numbers, we can produce any combination. So what BCD number system says us that they will provide you 4 bits. With the help of these 4 bits, you have to represent 0 to 9 like this. Only 4 bits you are provided, and you have to make the combo of 0 and 1 and produce 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now if the number is greater than 9, it means that it is not in the range of the decimal number system. Then it will be not considered as the BCD number system. And then what you have to do, suppose I have taken example of 19, then you have to split these numbers 1 and 9. 1 will be represented as 001 and 9, as you can see, 1001. Now the BCD number system is not really connected with today's topic of discussion, but I want you to know this for when you have to do some microprocessors program, there will be such unpacking numbers or packing numbers programs. Then you have to know the concept of BCD. That's why I've shared this with you for the sake of general knowledge. Now today's main topic, that how we can represent integers in binary form. Integers can be of two types, signed integers and unsigned integers. Unsigned integers are always positive, and the signed integers, they can be either positive or negative. There is not any sign in front of the unsigned integers. Okay, suppose I have taken 7 here. There is no sign, so we can denote it as plus 7. And it can be a plus in front of them, but it doesn't matter. Either there is a sign or not. If there is no sign, it is obviously denoted as a positive number, like 8. There is no sign in front of this, it means it's a plus 8. Now in case of signed integers, there is obviously a sign in front of them which denotes that either the number can be a negative one or a positive. Okay, so let us study that how we can store the positive numbers and the negative numbers. Suppose I have taken 3-bit signed numbers here. 3-bit means 2 to the power 3 equals to 8 combinations. Okay, so 8, 0 to 1, 2, 3, then minus 1, minus 2, and minus 3. 0 is considered in the the series of the positive numbers here. So I have written 0 to plus 3 here, and now we will know that how we can represent the negative numbers. The positive numbers are written as well it is. In case of the negative number, what will happen? The scientist has given us several methods. We will know the pros and cons of the methods. So first one is the sign and magnitude process. This process says us that we have to represent the number in this style. What it is? We know that the leftmost bit is called the MSB, right? In the MSB's place, if it is a minus number, then you have to put 1. And for the rest of the bit, it will be as it is, like minus 1. So if it's a minus, then you have to put 1 again, 1 here. Now for 1, it is like 1 0. In case of minus 2, it's here that's for minus it is 1, and for 2 it's 1 0, and for minus 3 for minus it is 1, and for 3 it is 1 1. Okay, but one thing you can notice here that we are missing a term here. What it is, if we can see the 8-bit combinations, the term we are missing here, it's 1 0 0, right? Now if we see that 1 0 0, according to the sign and magnitude process, this one denotes negative, and for the rest of the bits it's a 0. It will produce minus 0, which is not possible inside a CPU. What does this mean? That the sign magnitude process fails us to give the number combinations. Why? 2 to the power 3 means 8 combinations. So I have shown you the 7 combinations here, and the left combination, which is 1 0 0 in this case, is giving us minus 0, which is not possible with inside a computer. That's why sign and magnitude process will not considered as the right process. Now they have produced one more method, that is ones complement method. What we have to do for the positive numbers, it remains same, like 0 2 3 is always same. So for negative numbers, they say that put 1 in the MSB's place, it will denote that it's a negative number. And for the rest of the bit, like if I have taken minus 1, for minus you have to place 1 here, and the rest of the bits will be the ones complement of that respective positive number. So plus ones complement will be minus 1. Okay, let's have another example. For minus 2, plus 2 is 0 1 0. What will the ones complement of this? 1 0 1. Plus 3, it's 0 1 1. For minus 3, it will be 1 1 0. Okay, let's take another example. Suppose so for make you understand this, suppose 1 1 0. The MSB is 1, it means it's a negative number. Now the ones complement is 0 0 1. So this number is actually minus 1 if we follow the ones complement method. But as you can see, the combination that is missing in this process is 1 1 1. What is 1 1 1? For 1 in MSB's place, it's minus. Now I have to produce ones complement of this whole combo. It's 0 0 0, which means again this process is also giving us a minus 0. It also fails. Now the correct method and the right method is 2's complement. Let us see. Same for the positive numbers. What 2's complement says us that, as you can see, for minus 1, what we have to do? As it is a minus number, put 1 in the MSB's place, and plus 1's 2's complement is equivalent to minus 1. Like 0 0 1, its 2's complement is 1 0. I'm sorry, for minus 1 it is, as it is 1, so sorry, first we have to write the MSB. So minus 1 it is 1, and then 1 1. Okay, now let us do the minus 2. For minus there is in 1, and for 2 it is, like we have 0 1 0 here, so it will be 0 1 1. Okay, now minus 3, it will be 1 and 1 0. Okay, so we can say that here is also 7 combinations. The rest combination is the 1 1, the 1 1, sorry, 1 0 0. This combination is missing. What 2's complement says us? For the MSB it is a minus, and we have to do the 2's complement of this number. So 0 0 1's 2's complement is also 1 0 0, and what it is? It will give us minus 4. Okay, so 2's complement is giving us a whole new combo, that is minus 4. Now we can see that 0 to plus 3, 1, 2, 3, 4, 4 numbers, and minus 1, minus 2, minus 3 and minus 4. There is also 4 numbers. So if there is 8 combinations, there are 4 positive and 4 negative combinations. So if we follow 2's complement, we can store the minus numbers easily, and it is absolutely correct. Okay, so what we are getting here, 0 to plus 3 and minus 1 to minus 4. Now let me teach you tricks for 2's complement, as it is so easy. If we have to calculate a 2's complement of a number, what you have to do? Suppose I have written plus 5 here. Make the positive binary representation of plus 5. Now from left hand side, see where the first one occurs. When the first one occurs, write this as it is. And for the rest of the bits, it will be the 1's complement of them. So 0 it will be 1, 1 it will be 0, 0 it will be 1. Now again do this with me. 17. 1, 0, 0, 0, 0. Sorry, 1, 0. So it's the first one. It will be as it is. And for the rest of the bit, it will be the 1's complement of them. So 0, 1, 1, 0, 1. Now 9, for plus 9 it is 1, 0, 0 and 1. And for minus 9 it will be, so there is the first one. Let me write it is. And as it is 0, it will be 1, 1, 0. Let us do this again. Suppose it's a plus 6, for it is 0, 1, 1, 0. For minus 6 it will be. So let's come from right hand side. The first one is here. So before that we have to write as it is 0, 1, and now the 1's complement of them, 0 and 1. So this is the combination for minus 6. Okay. Now suppose if it is a 3-bit number, then it will be 2 to the power 3. It means 8 combinations, where 4 bits will be positive and 4 bits will be negative. So for negative numbers, we can say that it will be 0 to 4, and for 4 positive numbers it will be 1. Sorry, for positive numbers it will be 0, 2, 3, and for negative numbers it will be minus 1, 2, minus 4. Again for 16, 8 bits will be positive, 8 bits will be negative. So 0 to 7 will be positive, and minus 1 to minus 8 will be negative. Now 16, 0 to 15 will considered as positive, and minus 1 to minus 16 will be considered as negative. Same with suppose 2 to the power 16, 64. So 64's half is 32. So 0 to 31 will be positive, and minus 1 to minus 32 will be negative. Now here comes a special note. I'm sure that you all know C programming, right? So if we consider the integer parts, we know that there is always a range like minus 32, I don't remember the exact figure. Let me do this for you. In today's computer, the most of them are using a 16-bit data bus. It means 2 to the power 16, 65536 combinations will be there. So what is the half of 65536 divided by 2 is 32768. It means that if it is presenting unsigned integers, the range will be 0 to plus 3 to 767 combinations, and minus 1 to minus 3 to 768 combinations. And if it is a signed integer, unsigned integer, it will be like 0 to 65536. So if we have fixed some like a range, so half of them will be positive and half of them will be negative. So I think now you're clear that if we have to represent any negative numbers, we will always follow the 2's complement method. I've present some examples for you, because see, if we have to do Booth's algorithm or restoring the divisions, first you have to know that how the numbers are represented. Only then your whole algorithm will be correct. That's why I'm putting so much effort in this video, to make you understand the difference between these methods and all. So 5 can be represented as +5 and -5 also. So first you have to write +5, 1, 1, 0, +5, so the MS will be 0. For -5, what it will be? The 2's complement of +5. Now I have already told you the trick. For this, 1 will be 1. Now for them it will be 1's complement. 1, 0, 1. Now 67, 64, 3, okay. And there will be this 0 for like representing that it is a positive number. Now -67, 1, 0, 1, 1, 1, 1, 0, 1. 85, so 64, 8, 2, 1. Right? What it will be? 1, 0, 1, 0, 1, 1, 1, 0. And for positive numbers there is a 0, so in negative number there will be a 1. 26, 16, 8 and suppose, okay, let me do this. 8 to 4, 8, 16, 32. So 16, 8 and 2, 16 plus 10, 26. And there will be a 0 to represent it as a negative number, and minus will be 0, 1, 1, 0, 0 and 1. So this is -26. Okay, now just for your quick review, let me say this. Doesn't matter if we put infinite numbers of zeros in front of this, it will be still a +5. And for the 2's complement of this number, there will be so many ones, and still it will be -5. Okay, so that's it for this video. I will upload the rest of the numbers in my next video. Hope it will help you. And if you have any queries related to this video, please post in the comment section. Thank you.